Hi friends, this is Mira and welcome back to my channel. Today we will solve another problem on spheres and cylinders. We will find out magnitude of force and reactions acting on a cylinder to keep the body in equilibrium using Lami's theorem. Method to draw free body diagram will be discussed in detail too. So let's begin. Drainage construction work is going on along a road. Several concrete drainage pipes are laid along the shoulder of pavement which need to be transferred to the trench one by one. But before moving to the trench, pipes will have to be pulled over to the footpath first. And this is what our today's problem is concerned about. So let's have a look at the problem statement. A typical pipe of radius 300 mm and weight 2000 Newton is to be pulled over the footpath. Find the magnitude of force F required to just turn the pipe over the curb of footpath and hold it in position. Height of curb is 150 mm and force F is acting at 40° angle to horizontal through the center of gravity of pipe. It might seem like a ghost is holding the rope, but it's not. To solve this numerical, we will consider the side view of pipe by taking cross-section of pavement and footpath. First step is to draw the free body diagram by considering all the forces acting on the pipe. There can be three types of forces acting on a body while in equilibrium. One is external force applied. In our case, external force F is acting on pipe making 40° angle to x-axis and it will pass through the center of gravity of cylinder if extended. Second type of force is support reactions. Support reaction acts whenever an object is in direct contact to other bodies. In our case, pipe has point of contact A with the edge of curb. So if only curb is considered and if any free movement of pipe is restricted due to the curb, reaction of same magnitude but in opposite direction will be developed at this point A. Here, the pipe will be able to move in any direction freely under application of force but cannot pass through or push the footpath away. So the curb restricts this movement of pipe and so reaction R will be developed in the opposite direction. Before application of force F, pipe was touching the pavement too, but the force is applied such that pipe is little bit lifted so the contact with ground is lost and there won't be any reaction from the ground. No other body is in direct contact to pipe, so only one reaction R will act at point A. Now, apart from support reactions, one more force acts on object and that is self-weight W. Self-weight of object always acts in vertically downward direction through the center of gravity. So these three forces acts on cylinder. Remove the support and replace them by forces or reactions and this is the free body diagram. Now before calculating magnitude of forces, let's quickly find out angles all of them make with x-axis. We already discussed that force F is acting at 40° angle to x-axis and weight W acts in vertically downward direction making 90° angle to horizontal. Now only the angle reaction R makes with horizontal is missing. Here one important concept should be cleared. It is mentioned in the problem statement that the pipe is just lifted over the curb and it is not actually moving. So it is in state of equilibrium. As force F and self-weight W meet at center of gravity of pipe if extended, to hold the pipe in position and maintain equilibrium, reaction R must pass through the same point too. But why it has to pass through the same point? Let's understand. Suppose there is no footpath and pipe is just lying on pavement. If force F is applied and pipe is lifted, only two forces will be there, force F and self-weight W. So if resultant force of these two forces is to find out, according to the law of parallelogram, the resultant force Rf is the diagonal passing through the intersection point. Now with footpath considered, if reaction is not passing through the center of gravity, this system of forces will develop torque, which will start rotating the pipe, and pipe will no longer be in state of equilibrium. But if the reaction R is also passing through the same point, the horizontal and vertical components of both forces might nullify the effect of each other and resultant movement can be zero. So in any problem, if it is mentioned that the object is in equilibrium, then whatever number of forces may be there, if all other forces are passing through the same point, the remaining force will pass through that point too. Thus, the line of action of reaction R is same as line joining point A and center of gravity O, that is OA. And suppose R makes angle theta with x-axis. So let's find out this angle. First of all, join the line OA. Now try to make a right angle triangle by extending horizontal or vertical lines from O and A. Here horizontal line is extended from A and vertical line from O, and we get a right angle triangle. As R makes theta angle to horizontal, this angle is also theta and this is 90 degree. Now if you know length of any two sides of this triangle, you can easily find out theta using trigonometric equations like sin theta or cos theta or tan theta. Let's see how we can find it out. First length we can easily find out is the line joining OA or hypotenuse of triangle. We know that line from center to any point on circumference is equals to radius. So in our case, the hypotenuse is radius of pipe, which is given in problem statement, that is 300 mm. Length of one more side is required to find angle theta. Let's see what other data is given in question. Here the height of curb is given 150 mm. So using this detail, we will measure the vertical distance OB. Here as height of curve is 150 mm, length from point B to C is also 150 mm, and length O to C is radius, which is given 300 mm. So the length OB is radius 300 minus 150 equals to 150 mm. No horizontal dimension is given in problem statement, so it would be tedious to find side AB. But we have hypotenuse OA and opposite side OB available, so use equation of sin theta to find angle theta. Sin theta is equals to OB upon OA, that is 150 divided by 300 equals to 0.5, and so theta is equals to 30 degree. So R makes 30 degree angle with horizontal. If we drag force R along its line of action, this angle will be theta too. So if R is placed in such a way that its tail is at center, it makes angle theta equals to 30 degree with x-axis. Tails of all the forces are meeting at center. So now let's find out magnitude of R and F. As this is the problem of equilibrium, either Lami's theorem or equilibrium conditions can be used to solve the problem. Both methods give same result. We will find out forces using Lami's theorem. For this method, the very first step is to find out angles between adjacent forces. The angle between forces R and W is 30 degree plus 90 degree is equals to 120 degree. Angle between force W and F is 90 plus 40 is equals to 130 degree. Similarly, angle between forces F and R is total angle between positive and negative x-axis, that is 180 degree minus 40 minus 30 equals to 110 degree. Now, Lami's theorem states that if three forces are acting on a body, each force is proportional to the sine of angle between other two forces. Let's say first force is R and it is divided by sine of angle between other two forces W and F, that is sine 130. Second force is W and it is divided by sine of angle between F and R, that is sine 110 degrees. And third force is F and it is divided by sine of angle between R and W, that is sine 120. Then all these divisions are equal. Now the magnitude of force W is known to us, that is 2000 Newton, and magnitudes of R and F is to find out. So let's compare the equations of R and F with W individually. After putting all values, we get R equals to 1630.4 Newton and F equals to 1843.2 Newton. Let's solve the same example by a little change in question. Instead of direct pulling of pipe, a chain is wound around the circumference of pipe and F is applied in horizontal direction. If all other data is same, find out magnitude of R and F when the pipe is just lifted to move over the curb. Here also the pipe is just lifted and held into that position. It has not started moving. So again this is a problem of equilibrium. But only difference is F is applied in horizontal direction. So when it is extended, it will pass through a point on circumference and is not passing through the center of gravity of pipe. Again, consider the side view of pipe. Let's find out all the forces acting on pipe and their direction of application for this case. External force F is acting in horizontal direction, making 0 degree angle to x-axis. Self weight is W, which is acting in vertically downward direction through the center of gravity O, making 90 degree angle to x-axis. Now, if the line of actions of weight W and force F are extended, they meet at point C. Third force is reaction from curb R acting at point A. Here, as all other forces, that is force F and weight W are intersecting at point C, line of action from R must pass through the same point C to maintain the state of equilibrium as we discussed in previous problem. Otherwise, the system of forces will produce torque and start rotating the pipe. So, R must act along the line joining point A and C. Now let's find out angle it makes with horizontal. First of all, join the line AC. In previous problem we calculated angle line OA makes with x-axis, that is 30 degree. Extrude a vertical line from C to B to make triangle. Now we know that for a triangle, inscribed angle, that is angle at circumference, is half of central angle. So in our case, suppose this angle is phi, the angle R make with y-axis is equals to phi by 2. So let's first of all find angle phi. For triangle OAB, this is right angle, and so angle phi is 90 minus 30 equals to 60 degree. So angle reaction R makes with vertical axis is phi by 2 is equals to 60 by 2, that is 30 degree. This is the angle between R and Y axis. So if we want to find out angle with X axis, it is 90 minus 30 equals to 60 degree. Again, if we drag force R along its line of action, this angle will be 60 degree too. So if R is placed in such a way that its tail is at center, it makes angle 60 degree with x-axis. Tails of all the forces are meeting at center. So now let's find out magnitude of R and F. The pipe is in state of equilibrium, so we will find out forces using Lami's theorem. First step in this method is to find out angles between adjacent forces. The angle between forces R and W is 60 degree plus 90 degree is equals to 150 degree. Angle between force W and F is 90 degree. Similarly, angle between forces F and R is total angle between positive and negative x-axis, that is 180 degree minus 60 equals to 120 degree. Now Lami's theorem states that if three forces are acting on a body, each force is proportional to the sine of angle between other two forces. Let's say first force is R and it is divided by sine of angle between other two forces W and F, that is sine 90. Second force is W and it is divided by sine of angle between F and R, that is sine 120 degree. And the third force is F and is divided by sine of angle between R and W, that is sine 150. Then all these divisions are equal. Now the magnitude of force W is known to us, that is 2000 Newton, and magnitudes of R and F is to find out. So let's compare the equations of R and F with W individually. After putting all values, we get R equals to 2309.4 Newton and F equals to 1154.7 Newton.